All right, great. Our team is eGlove. We tried to get three things done. So first, our most ambitious goal was to predict the continuous fingers flexion. And then we wanted to see if we could classify hand gestures, but this time using independent components in order to reduce the load on real-time interfaces. And also, we did the comparison between different machine learning techniques in the classification task. So for the first task, we noticed that when we look at the wavelet transform, we noticed that the desynchronization happens when there is an activity of the fingers, the finger flexion. So we thought maybe we can use the frequency domain as input for our LSTM model, and the output would be the time series of every finger flexion graph. However, the LSTM model took too long to train, so we don't have any concrete result for this particular goal. For the next goal, we tried classification, but we wanted to use independent components. So we did a very light pre-processing just to remove the drift and the line noise. And then we epoch the data -1 second before the onset and then 3 seconds after the onset. Then we applied ICA and we chose ICs that looked promising just by observing the ERP. And finally, we applied logistic regression for the classification. As you can see here, here we see the ERP of the independent components. The red ones show the most prominent ERPs, and the blue ones show some activity. The rest was just discarded. And for the classification, so one time we used the 7 independent components, and one time we only used the red ones. And we noticed that the average to test the model, we used the leave one out cross validation. For when we used the 2 ICs only, we got a classification accuracy of 64.45%. And when we use the 7, also we got the same thing, which means that the 2 prominent ICs capture most of the information about the hand gestures, which is really good. We can really reduce the load of in real-time devices, because with only 2 stream of independent components, we can get reliable classification. For the third part, we tried to stick to the processing that was in the original paper. We downsampled to 600 hertz. We only choose the gamma band from 50 to 300 hertz. And we compared between LDA's random forest and SVM. We found that random forest performed better than the rest. After that, we tried to explore the features a bit more. So we plotted the feature importance plot. And as you can see here, there are some frequencies that are more important than the others. So we just repeated the classification using only those frequencies. So here you can see the classification result when we use the frequencies from 30 to 500, 50 to 300, and it's about 70%. And when we use the frequencies only from 75 to 125, we got almost the same classification, which means we can also reduce the load on real-time machines using only this frequency band. So yeah, we were all working remotely from different countries, so this is all the best picture we could find. What could have been useful for us if we could get the channel's location. That way we would have been able to localize the independent components. And then we would probably be able to pick up better components that would give us better results. And we could have also used more processing power or we could have used some models that were already pre-trained, and we just would fine-tune the model. That's it for us. Thank you for listening.